nanohub.org.
Online simulation and more for nanotechnology.
Okay, good afternoon, everyone. So thank you for coming out on the last day of winter. Right? I'm sure this is the last snow. So I want to welcome, we're very fortunate to have Shalu Rakaji visiting us from MIT. So I've gotten to know Dr. Rakaji through the NEEDS program. So we've been interacting closely on a number of different projects. She did her bachelor's degree in IIT Kanpur, I believe, in India. Yeah. Grew up in a small town, maybe even smaller than Lafayette.
Yeah, it was pretty small.
Oh, okay. And then did her master's and her PhD at Georgia Tech. So working on alternative switching technology, focusing on interconnects for both electronic devices and spintronic devices. And for about a year, I guess she's been at MIT as a postdoctoral student, working with Dimitri Antoniadis on a variety of different problems, including novel transistors, but she's also continues to be involved in work on graphene and spintronics and other topics. So it's the graphene work that she's going to be telling us about today. Mm-hmm. So welcome to Purdue. We're looking forward to your talk.
Thank you, Mark, for such a kind introduction, and I'm really happy to be here. Some of the people that I have actually looked up to all my life as a PhD student are here, and I feel extremely fortunate to be here. And welcome to my talk on the role of graphene in semiconductor technologies. Before I get started, I'll tell you a real story of how I got involved in graphene. When I first joined grad school, I started working in electrothermal modeling of carbon nanotubes. And then graphene was a fairly new material at the time, and people were still discovering its exotic physical properties. And we were struggling a lot at the time with the interconnect problem. Not that the problem is solved now, but I started looking at the potential of graphene for interconnect applications. And the more I worked in graphene, the more I realized that it had the potential for a lot of different kinds of applications. But one of the things that people don't realize is that graphene technology actually opened doors to a lot of novel 2D technologies that can be put to use in future for future applications. So in this particular talk, I'll try to tell you the things that I have worked in graphene and the projects that I am really interested in going forward. So graphene is an atomically thin layer of carbon atoms arranged in a honeycomb lattice, and it has applications in electronics like on-chip interconnects and even RF circuits. And it can also be used for flexible electronics like solar cells, touch screens, sensors. And integrating graphene with silicon photonics is a very important research direction, and you can build active devices like photodetectors and optical modulators. And even for health purposes, you can actually attach a lot of chemical molecules on graphene and make it more or less soluble and guide it towards a specific therapeutic target. So graphene, as you see, has a lot of different kinds of applications. And in this talk, I will focus on electronics, which is on-chip interconnects and radio frequency circuits. So I've partitioned my talk into 3 distinct components. In the first part, I'll motivate you as to why graphene makes sense for interconnect applications. And towards this end, I'll go over electron mobility in graphene. I'll be giving you a specific example of multi-layer graphene interconnects, and I'll be showing you some of the advantages, limits, and opportunities of graphene interconnects as compared to copper interconnects at advanced technology nodes. In the second part of my talk, I'll go over a specific model that we call the virtual source model that I've developed for radio frequency circuits. It's a static transport model that is also supplemented by a dynamic charge partitioning model. We've done a lot of exhaustive experimental calibration with data from MIT, Columbia University, and also from IBM. In this talk, I'll be focusing on the new data that we got from IBM. And then I'm going to bridge gaps between the virtual source model and the model that Mark proposed based on reflection and transmission coefficients, and try to extract some meaningful parameters for this technology, such as mean free path, effective mobility, and ballistic velocity. At the end, to demonstrate the model capability for circuit and system level analysis, I'll be showing you Spectre simulations of frequency doubler circuits with graphene devices. And some of the topics that I'm interested in the future are related to graphene solar cells and integration of graphene with silicon photonics, photodetectors, and modulators. So before I get started, I want to spend exactly 1 slide to explain to you what the interconnect problem is. So microprocessor technology has benefited a lot from dimensional scaling along Moore's law. Moore's law is a law of economics, not a law of physics like the Newton's law. It tells us that if you shrunk your devices by X percentage every couple of years on the microprocessor, you would increase binary information throughput and make more money for the industry. Very good. And in fact, that has been the mantra behind dimensional scaling for a number of decades, which increased the transistor performance, but sadly degraded the interconnect performance. Interconnects are these metal wires typically implemented in copper in a microprocessor that communicate information between point A to point B on the chip. So let's say you were trying to do some computation and you wanted to transmit information from location A to location B, and if you couldn't do that in an energy efficient and a fast way, then that would pose a bottleneck for this technology. And at the same time, you see that in a microprocessor, more than 50% power is being consumed in the interconnect. So the idea is that interconnects do place latency and power demands on the microprocessor, and I have no idea why this is automatically getting switched. So let me just do something here. Okay, so interconnects do place latency and power demands in the microprocessor technology, and graphene can actually play a role over there because of several of its advantages like high electron mobility, low per unit length resistance, lower capacitance. It has a very good current carrying capacity, and it can be integrated within existing semiconductor technologies. Here's a plot that shows per unit length capacitance versus technology of both copper and graphene nanoribbons that I acronym as GNR. So every time I use GNR, it stands for graphene nanoribbons. And you can see that the per unit length capacitance of graphene nanoribbons is much less than that of copper, and therefore you can implement low power interconnects with graphene ribbons. But the question is that to be able to quantify the performance limits of this particular novel technology, you have to understand the graphene material, both its intrinsic and extrinsic properties. I'll get started with the intrinsic properties of electrons in graphene. So the intrinsic limits are imposed by scattering due to phonons, both acoustic and optical phonons in graphene. And here is a plot that shows the mean free path versus carrier concentration in graphene. And at reasonable carrier concentrations, you can see that the mean free path can be as high as 1600 nanometers. And in fact, this was the mean free path that Bolodin actually measured in his graphene devices, but those devices were actually suspended between two contacts and there was no substrate on them, right? So such high mean free paths can be obtained, but for real circuits, you have to deposit graphene on a substrate. And you also have to pattern it into narrow ribbons for real circuit applications, and both of them will lead to an interaction of electrons with edges, with the phonons in the substrate and with the charged impurities, and will lead to a degradation in the mean free path and the mobility of electrons. And those are some of the realistic effects that we need to incorporate in order to assess where graphene lies in this whole landscape of interconnect applications. Here is an STS measurement of graphene on SiO2, and you can see that it's very rough, and there are formation of electron hole puddles that also causes smearing of the Dirac point. And the top picture is a TEM image of edge states in graphene, which was done by UC Berkeley in 2011, and edge states have different energy states and they lead to a lot of degradation in mobility. So in our models for electron mobility, we have incorporated all of those realistic effects, but instead of getting into complex mathematical equations, what I'll do is I'll try to present the final results and tell you some of the implications that it can have for interconnects. So this plot over here is mobility of graphene on various substrates. The different traces on this plot correspond to graphene being deposited on different kinds of substrates. So I want to focus on the topmost trace over here, that is the light blue color, if you can tell. And the mean free path over there is about 300 nanometers, and that is hexagonal boron nitride. And graphene on boron nitride has the highest mean free path, highest mobility, because boron nitride is an isomorph of graphene, and what I mean by that, it is lattice matched, and therefore it leads to less degradation. But still, 300 nanometers of mean free path is about 1/5 of what you could get if graphene was suspended between contacts. So we see that these are some of the serious limitations of substrate interaction with graphene that needs to be included. We have good match with experimental data as well for our models, as you can see by some of the symbols that I've put on this plot. Next, what I wanted to do was understand how the patterned graphene edges would affect the mobility of electrons in graphene. So when you pattern graphene into narrow ribbons, it makes the edges rough, and that causes diffusive scatterings of electrons at the edges, which is modeled through an edge scattering coefficient called PGNR, which lies between 0 and 1. 0 is the perfect case of smooth edges, and for diffusive edges, PGNR assumes the value of unity. So this is a plot that shows mobility versus width in a GNR, or a graphene nanoribbon. Don't worry, it's a very busy plot, but I'll walk through all of the different sets of traces over here. If you look at the topmost two traces, that correspond to graphene being deposited on an extremely good substrate that does not introduce any additional scattering effects, and also there are no edge scattering effects, and you can clearly see that the mobility is in excess of 10,000 centimeters square per voltsecond, which is very good. The next two set of traces, which are these blue traces, they correspond to graphene being deposited on a real substrate like boron nitride, and you can now see that the mobilities are limited to only few thousands of centimeters square per voltsecond. Finally, when you open the edges, when you make edge roughness, when you include the effects of edge roughness, you see this sort of a roll-off of mobility with the width of the ribbon. And that can have serious implications for interconnect applications. And you see that for an interconnect width, which is less than 10 nanometer, the mobility would be limited to only few hundred centimeters square per voltsecond. An important parameter that we have to consider for interconnect applications is the sheet resistance, or the per unit length resistance, because that determines the delay of the interconnect, or the latency, which is an important factor for us. So a degradation in mobility would definitely lead to a degradation in that sheet resistance, or the per unit length resistance that we're talking about, and that I will talk about in the next slide. So this is an N-layer graphene interconnect. I call it the multi-layer graphene nanoribbon, MLGNR, and it's between two contacts, and it's deposited on the substrate. The in-plane resistance is R layer, the perpendicular resistance is R perp. Now R perp, which is the perpendicular resistance in the structure, is much higher than the R layer. If we zoom in on this image a little bit, what we see is when electrons are trying to come in from the contact into the interconnect, there is a mode bottleneck because of the mismatch in dimensionality between the contact and the interconnect. Contact is a three-dimensional material, and the interconnect in graphene over here is two-dimensional. And not only that, the electrons only want to flow in the topmost layer. Why? Because current wants to take the path of least resistance, and as I just mentioned, the perpendicular resistance is very high, and therefore the electrons don't want to penetrate into the deeper layers. So what we really expect is that the distribution of the current would be non-uniform in this vertical interconnect structure. Now, most of the experiments that are done in multi-layer graphene interconnects with top contacts naively assume that these contacts are coupling equal to all of these perpendicular layers, and that actually overestimates their performance. So what we realized was that these bottleneck issues, this non-uniformity of current distribution, is an important effect for interconnect applications that we need to incorporate in our models. So here is a simulation, MATLAB simulation of the distribution of current in a multi-layer graphene interconnect. We've considered two interconnect lengths. The dashed one over here is 5 micrometers, and the solid line is 10 micrometers. What you see over here is that shorter the interconnect, the more non-uniform the current distribution is. And that is sort of, you can explain that by saying that for shorter interconnects, the in-plane resistance is much lower, so the current now really wants to flow in the top layer, and it doesn't really want to go into bottom layer. And the take-home message is that the performance evaluation of these interconnects must incorporate imperfect coupling of contacts and graphene. The topmost circuit over there is the schematic of the driver interconnect receiver that we are using for evaluating the performance of these interconnects, and the bottom circuit shows the equivalent circuit corresponding to that, where the interconnect is represented by a distributed RC network, which is over here, this one, and the points that I've labeled as C1 and C2, these are the contacts between the driver and the interconnect, and they do take into account mode bottleneck issues. The delay is given by the expression over here. There are three distinct components in the expression. One is the first part over there is independent of the interconnect length. That is the length through which you are trying to communicate information. It is mostly limited by the source or the driver resistance. And then we have a part that varies linearly with interconnect length. And the third part is independent of the interconnect length. For short local interconnects, it's the first two components that matter a lot. The third component is not that important. And it's the short local interconnects that we are trying to target over here instead of the long back end of the line, like the topmost layer. We're not targeting that. And the energy dissipation is simply given as the amount of energy that would be needed to charge or discharge the total capacitance at the output node. So let's look at what happens to the delay versus the technology here. This plot has both copper and graphene delay with side contacts and top contacts. The interconnect length that I'm targeting over here is 10 gate pitches. One gate pitch is the average footprint of a 2-input NAND gate on the microprocessor. So this is very interesting. When you see side contacts, this is what people predicted. Okay, graphene is really good, it has great sheet resistance, and therefore it will perform better than copper, which is what side contacts, the red line shows. The black one is the copper one. But if you have these top contacts where the current is really not coupling to all of the perpendicular layers, you will see that graphene starts to behave worse than copper at advanced technology nodes. So the key message over here is that size effects and improper contact couplings will tend to hurt multi-layer graphene interconnects quite a lot at advanced technology nodes, and this needs to be incorporated in all of the technology assessment that we do with these interconnects. The next plot over here is the energy delay product versus technology here. And we see that both side contacts and top contacts perform better than copper interconnects. And the reason for that is the graphene interconnects really have lower capacitance, and therefore they can beat copper in terms of energy delay product or even in terms of energy, right? Still, you can see that top contacts are not as good as side contacts. So that was the whole point of assessing the advantages, limits, and opportunities of these interconnects by taking realistic effects into account. So to summarize part one, I've very briefly showed you that graphene does have the potential for on-chip interconnect applications, particularly short local interconnects. But at the same time, you have to take into account substrate coupling. You have to take into account the effects of edge roughness and, mode bottleneck, imperfect coupling. And then only you can assess the real advantages, limits, and opportunities of any technology. So this was just to motivate you to the fact that any kind of real circuit applications, when you're targeting, you really have to understand what is going on at the fundamental physical level. So next I'll move on to graphene. Yeah, sure.
So for the delay, like a plot, so you are calculating the resistance times capacitance, right?
Well, that is when resistance times capacitance for the interconnect is valid only for very long interconnects where the source resistance does not play a role. But for short local interconnects, if you're using these advanced transistors really have very high resistances, so those need to be taken into account. So the delay has three components. One is independent of length, the other is linearly with length, and the third one is quadratically with length. So what we are targeting is the first two components where it's either independent of length or linearly dependent on interconnect length.
For the graphene, the resistivity is almost 2 to 3 orders of magnitude higher than copper. So at the end, why the delay is only like
No, so over here, it depends actually. I really see your point. But over here, what we're doing is we're assuming that the graphene is deposited on a very good substrate like boron nitride that has a very high mean free path of 300 nanometer. And even the mode bottleneck issues that I'm talking about, contacts, we're assuming a transmission coefficient of about 30%. So you can see, and that it's sort of, an optimistic way of looking at it. But even at this optimistic way of looking at it, we see that graphene does not do a very good job at advanced nodes. So if you were to take graphene on SiO2, for instance, it would be much worse. Or if the edge roughness was more, it would go even like it would have a much higher latency than copper. So these are like optimistic, yet we have incorporated some of the realistic effects that matter to us.
And also for the common resistance that you are considering between the bilayer graphene, like that you are saying the current distribution actually not gets impacted. What is the common resistance?
I'm sorry, I don't remember the values off of my head right now, but I can show them. I can discuss that with you later. But it's kind of very, very high.
How do you deposit this graphene? Is it CVD graphene or mechanical stability?
I'm not an experimentalist, but graphene can be done through CVD or exfoliation as well.
Because typically CVD graphene has very low values of mobility.
Yeah.
So just wondering, in these calculations, have you taken high values of mobility first?
So what we're doing in these calculations is we looked at a couple of different substrates as I showed you earlier. We have all of these different substrates, but the plots that I showed you for delay were only for graphene on boron nitride. And like I said, if you did analysis with more experimental data, you would actually end up getting much worse performance results for graphene. And sometimes you want to show people good and the bad with a mixture. So this is what my point is, that there are bads and there are goods as well. So.
May as well get all of the questions about interconnects out of the way here before you go on to transistors. So help me. So I think your conclusion is graphene could be better than copper.
For energy.
Okay. And it's, if I understand correctly, it's not because of sheet resistance, it's because of capacitance. Is that right?
Graphene can be better.
Capacitance, why is it lower than copper? Is it because it's thin?
Thin.
Okay, so there's less of a sidewall.
Yes. It's very thin. So what we're doing for graphene capacitance in these devices, when I published these results, we did not include quantum capacitance effects into account. We had only electrostatic effects, but we now have a full simulation that takes into account the capacitance between the layers, quantum capacitance and all those effects. But the conclusions are pretty much unchanged, that it has a lower capacitance.
And then one simple question on this pie chart you showed near the beginning. You had about 50% of the power dissipation was due to the interconnects. About 25% was due to gates. That must be
the charging, discharging, and the rest of
diffusion.
Parasitics. It's parasitics. It's when Intel people did this, they called it diffusion, so I didn't want to change it. And I think they're talking about parasitics because now for advanced technology nodes, the parasitics are almost equally high as your actual gate capacitance. They're becoming very, very important. So I think that is what they're talking about. But that is all related to the gates.
So my question is that even if the capacitance is there, smaller, but the resistance, the resistance in the copper should be smaller because you have a thickness. You can increase the thickness and the resistance will go lower. But in the graphene, you just have 2D. So RC, I didn't guess that.
That was the point. The point is that for RC or for delay performance, graphene does not really compare very well against copper interconnects. And we were targeting very short local interconnects. And even for short local interconnects, the conclusion remained pretty much unchanged. So for capacitance, yes. So we tried building, in SPICE, not in actual circuits, subthreshold circuits with both carbon nanotubes and graphene because they have low capacitance and they could actually beat the traditional.
What is the motivation? Because the graphene nanoribbon is not a metal ribbon. It's a semiconductor. So
it's not a semiconductor, it's a semi-metal.
The bulk is semiconductor.
Yeah. You have a little bit of a band gap, yeah.
So it's not, at the first look, it doesn't look like a good candidate.
Well, for interconnect applications, unfortunately, you have to pattern graphene into nanoribbons. So that unintentionally opens up the band gap. And people have argued that zigzag versus armchair, one of them would be metallic and the other would be semiconducting. And I beg to differ because none of the experiments have shown metallic characteristics. So that is also one of the limitations. While for transistor applications, you want a band gap, for interconnect applications, you don't want a band gap. So, yeah. It's sort of limiting. But the motivation came from the fact that in many ways graphene was similar to carbon nanotubes when we started exploring the potential of carbon materials for interconnects. So we wanted to see how graphene could help us. All right. So not all research results lead to positive results. I think that finding the limitations of a technology is also very important to guide the experimental research in the right direction.
Need to find an ideal layer thickness in your structures?
Yes, we have. So this one, the plot that you are showing us, I showed you over here, was computed for an ideal optimal number of layers for delay performance. And the thing is that as you keep on increasing more layers, the performance benefits don't scale with the number of layers. So we did all of that analysis. And you know the paper very well, so I think.
And it turns out for those ideal ones?
Yeah, for those ideal ones also they have these limitations. That's what I said, that, yeah, for ideal ones also a lot of limitations. All right, so I'll shift gears and move on to graphene for analog RF circuits. This is the work that I did last year at MIT. So for RF, this is a graphene with 2 gates, graphene transistor with 2 gates. We have a top gate and a back gate, and it's on a back oxide, which is typically SiO2, and it can be done through CVD or exfoliation. The typical transfer curve of a graphene field effect transistor looks something like that, and it has a minimum conduction point, which we call the Dirac point. And to the left of this Dirac point, we have the hole current, and to the right of the Dirac point, we have the electron current. And this is an ambipolar transfer characteristic, and it's very interesting. This novelty of graphene does not exist for silicon transistors, which are unipolar transistors, and we can use this for building frequency doubler circuits with a single device, something that is not possible with silicon transistors. Another feature that emerges from this particular plot is that you see that the electron and the hole branch currents are asymmetric. And this asymmetry arises typically because of the way the source and drain contacts couple to the electrons and holes in the graphene layer. They couple very, very differently. So if I want to simulate a frequency doubler circuit, the first point over here would be, coming from a circuits background, people would say, okay, where is the model file? Give me the model file. So we need to develop a compact model to explain the transistor characteristics. And I think there are 3 essential features that any compact model should have. The first one is that it should capture the essential physics at the nanoscale transport, and it must be a compact analytical description. We don't want to run numerical analysis. And the third one is that it must be true to experiments. So the model that we have developed for graphene field effect transistors, which we call the virtual source model, accomplishes all of this and more. It's a quasi-ballistic transport model that goes all the way from drift diffusion to ballistic regimes of transport. It is ambipolar, and it also comprehends the asymmetry that is introduced due to different electron and hole channel access resistances. And finally, we have supplemented the model with a self-consistent channel charge model. But before I get started, I'll take one slide. You want to ask? I'll take one slide to explain to you the physics of the virtual source model. The top picture over here is a field effect transistor with all of its terminal voltages labeled, and the bottom picture is the profile of the conduction band as a function of position within the channel, and the point labeled as X0 is called the top of the barrier, or as we commonly call the virtual source point, and VXO denotes the velocity of carriers at the virtual source point. The current in saturation is simply given as the product of the charges at the virtual source point and the velocity of these charges at the virtual source point. Then we multiply this with an empirical function fsat to achieve transition from saturation to linear regimes of transport. Fsat is mathematically implemented in a way that it goes to unity when the transistor is in saturation, but I won't have time to get into the implementation of fsat, but I still want to point out that fsat depends on the drain to source bias, it depends on mobility, the gate length, the injection velocity, and there is this parameter beta, which actually can be obtained upon calibration with experiments. So that is an empirical parameter. How is this model applicable in graphene? Graphene is very unique because it is gapless material, and therefore there exist 2 virtual source points at opposite ends of the channel. The picture on the right shows the electrostatic potential profile in the graphene channel. The point labeled in blue is the virtual source point for electrons, and the point labeled in red is the virtual source point for holes. Note that even though I've called both of these points as X0, these exist at opposite ends of the channel. And because of the perfect symmetry between the conduction and valence bands in graphene, the virtual source injection velocities for both electrons and holes are identical, and we call them VXO. So the current is simply given as the superposition of the electron and the hole branch currents. And again, we have the function fsat over there to achieve this transition from saturation to linear regimes of transport. So if we have QXO and QXOH as functions of the terminal voltages, we'd pretty much be done with our compact model. So how do we come up with compact models for QXO and QXOH? We were basically inspired by silicon materials with a band gap. So the expressions that we've adopted are typically valid in materials with a band gap. The advantage of these expressions is that the model can very naturally be extended to bilayer graphene where a band gap can be opened. And the expressions are given over there. I'll point out a few essential features in these expressions. Q dis that you see over there on the right side, that is the disorder-induced charges, which basically exist in graphene because of these electron hole puddles. And VTN and VTP, these are the threshold voltages corresponding to the electron and the hole branches of current. And we have a few fitting parameters over here. The first fitting parameter that goes in these expressions is N, which is related to the subthreshold slope of these devices. And then we have a fitting parameter alpha, which basically governs the shift in the threshold voltage from subthreshold to strong inversion operation regimes. And we also have delta V over here, this one. That basically approximates the effect of trap charging, interface trap charging. And we have FFE and FFH, which are Fermi-like functions. So a question that you would ask me is, how do you know that these expressions are valid in graphene? And to answer this question, we did numerical computation of charges by exploiting the concept of voltage divider networks at both the virtual sources for electrons and holes. In a quasi-ballistic transistor, the concept of virtual source, this voltage divider network, is indeed valid at the virtual source points, even though it may not be valid within the rest of the transistor. And the voltage divider network for electrons is here, and Cg is the oxide capacitance. Cq is the quantum capacitance, which depends upon the surface potential. And likewise, we have a similar structure for the holes, and there the quantum capacitance depends upon the surface potential at the drain end. So what we did was we used Fermi-Dirac integrals and voltage divider networks to compute the charges numerically. Another thing that goes into this computation is the density of states, and we have to use an appropriate density of states for these calculations. What I mean by appropriate density of states is a density of states with a broadening function that can actually simulate the effect of electron-hole puddles in graphene, and then you could compute your charges numerically. I'll show you some comparison results of charges that were obtained using numerical and our compact modeling approach. So that shows the net charges in the channel at the virtual source point versus the gate voltage. We have 4 traces over there. The 4 traces correspond to 2 different values of the equivalent oxide thickness for the gate and 2 different values of the broadening for energy for density of states. So sigma over there is the broadening in the density of states. The symbols have been obtained using the numerical model, and the lines have been obtained using the compact models. They actually, it looks very good. So in the compact model, we've adjusted Q-dis, which is the disorder-related charges, and we've also made some slight adjustments in the equivalent oxide thickness in the compact model to come to this. And we've fixed n equal to 2 and alpha equal to 6 for this particular plot over here. Next, I'll show you the adjustments that we've done in Q-dis, which is the disorder charges, and the equivalent oxide thickness to come to this result. So Q-dis, which is the disorder-related charges, versus the broadening in the density of states. So we see that if you look at the dashed line, that is for an equivalent oxide thickness of 15 nanometer, and we see that the disorder-related charges were fixed between 1 to 3 times 10 to the power 11 per centimeter square. And the EOT was adjusted within plus minus 10% of its physical value. So we have sufficient confidence in our compact models that we are using for charges. And we did actually a very comprehensive least square curve fitting analysis to come to this particular result. So I think it gives us a lot of confidence in what we are doing. So asymmetry in current conduction is another important aspect of graphene transistors. And this is a typical transfer curve of epitaxial graphene for a 3.5 micron long transistor. And we see that for the same shift about the Dirac point, the electron branch current is more than the hole branch current. And we know that the mobility of carriers in these devices should be roughly same. At least the intrinsic mobility should be the same. And also the virtual source injection velocity of the carriers should be the same because of the symmetry between the conduction and valence bands. So how does this asymmetry really arise? It arises because of the difference in the channel access resistance for electron and hole branches. So the top picture over there is the field effect, the graphene field effect transistor now connected to its source and drain resistances. Both RS and RD are different for electrons and holes. And in our model, we have indeed included 2 different resistances called R-elec and R-hole, which can be obtained upon calibration with the experimental data. So I'll show you a phenomenological circuit model to capture this asymmetry. RS is implemented by this bottom circuit block shown over here, and RD is implemented by the top circuit block shown over there, and both of them are exactly symmetric. You can see from this that I-hole, which is the whole branch current, is affected only by R-hole, which is the whole channel access resistance, and likewise I-elec is affected only by R-elec. And also you should note from this particular implementation that this now makes RS and RD non-linear voltage dependent resistances. And here is our simulation result for the transfer characteristic of a particular graphene field effect transistor. Here I fixed the R elect to 500 ohm microns and R hole was changed. When R hole is changed, you can clearly see that the current in the whole branch and the current in the ambipolar region, this is the ambipolar region around this point over here. Only those regions are affected. Why? Because holes play a significant role only in those regions. In the electron side, it's electrons that are carrying the current, the majority of the current, most of the current. So that part is really not affected. So with this slide, I'll conclude my findings on the static transport model and I'll go on to the dynamic model. What does the dynamic model mean? Dynamic model actually gives us the charges at the different terminals, the source terminal, the drain terminal, and the gate terminal. We are using the Ward-Dutton charge partitioning scheme, which is valid irrespective of whether the transport in the channel is drift diffusive or ballistic, as long as quasi-static transport conditions are maintained in the channel. And QS and QD are given by the expressions shown over there. And in those expressions, we have QHX, QEX. Those are position-dependent electron and hole charges in the channel. And at low VDS, you can still model your transport as drift diffusion with no velocity saturation, which is what I acronym as DDNVSAT. And then finally, once we have the quasi-ballistic charges, we blend them with the drift diffusion charges using the same FSAT function that we've used for transport formulation. So I won't actually get into how we've implemented these drift diffusive charges, but I'll get into how we've implemented the quasi-ballistic charges because that is important and that was the missing link in all of the previous modeling efforts that were being done in graphene field effect transistors. So how do you compute the quasi-ballistic charges? We use actually two conditions, two physical conditions over here. The first is the condition of current continuity for both electron and hole branches, which are given by the two expressions over here. The left-hand side in these expressions is known to us because we've done the transport formulation, the static transport formulation. We don't know the right-hand side. But if we can find the position-dependent velocities, which are VEXX, VHXX, we can come up with the position-dependent charges, go back on the previous slide, do our integrals, and come up with all of the charges. And to come up with position-dependent velocities, we are using the condition of energy balance. And I won't get into the math, but those are the two equations that give us position-dependent velocities. To me, the most important parameter that goes over there is this zeta over here. That actually is the fraction of the VDS energy gained by carriers as they travel along the channel. So if it was a perfectly ballistic transport, zeta would attain its highest value of unity. For any quasi-ballistic transport, zeta will lie between 0 and 1. So I call it the ballisticity parameter or a measure of the ballisticity in the channel. I'll show you some simulation results of charges versus the gate to source voltage for these devices. This was done for a 210 nanometer device. The drain to source voltage was fixed at 1 volt. And you can clearly see that the charges change their polarity as the transport changes from one carrier type to another carrier type. And that's what I've been emphasizing. The graphene is ambipolar. It can have either electrons or holes depending on the voltage regime that you're trying to operate. And the ballisticity parameter was fixed as 30% in these devices. Now the question is, if you used a drift diffusion formulation, what would happen to the charges? This is what would happen. The DDNVSAT charges would be overestimated. So the drift diffusion needs more charges to generate the same amount of current, and therefore it will lead to an estimation of all of your charges. And this can have serious implications for your device performance, because now charges are more, capacitances will be higher, right? So once you have the charges as a function of voltages, which is what I explained to you, now you can come up with capacitances as functions of voltages using the expressions given over here. I'll show you a typical example where we did the gate capacitance simulation versus the gate voltage, and we have both the drift diffusion charges and the quasi-ballistic charges. The bunch over here are quasi-ballistic and the top ones are the drift diffusion charges. And that's what I've been emphasizing, that the drift diffusion charges are always overestimated and therefore the capacitance is also overestimated. And there's another interesting feature that emerges from this, which doesn't really happen in silicon. And that is the appearance of that hump. In silicon, you will never see capacitance doing something like that. And over here, you see something like this. And that's only because current is being carried by both electrons and holes in graphene. So if you actually biased your transistor somewhere over here or somewhere on the other side, you would get a higher current gain, right? Because now current gain depends on capacitances. So if the capacitances are lower, you would end up getting a higher cutoff frequency, higher current gain. But as I'll talk about in one of the later slides, for frequency doubler applications, you have to bias your transistors at the minimum conduction point. So that's a challenge. So with this slide, I conclude my findings on the dynamic model, and I'm going to move on to experimental calibration. All right, so we did experimental verification with a lot of different kinds of devices. For the IEDM paper that I did last year, we used data from MIT and Columbia University. Over here, I'm showing you the data from IBM. These are epitaxial devices which are done on silicon carbide. And they were very generous to give us data for gate lengths ranging from 650 nanometer all the way to 40 nanometers. Now, these are the output curves of 650 and 300 nanometer devices, and the symbols are the experimental data, and solid lines have been obtained using our model. We see that an extremely good match is obtained between the two, and we were able to extract some of the parameters in the model in a physically meaningful and realistic way. This is the data for 140 and 40 nanometer channel length devices. This is again output data, and we again see a very good match between the experiments and our model. We've used an exhaustive numerical least square curve fitting analysis to extract all of our parameters, and obviously one would always ask me, how can you extract them? Because there's always interaction between the parameters in a model, and that's a discussion probably for another time, but we have significant confidence in the parameters that we are extracting using our numerical implementation.
How many total parameters are involved in this kind of thing?
So in this, overall we had 7, but having said that, I did a lot of sensitivity analysis to remove certain parameters, like I'm not optimizing beta, for instance. I'm going to take the electron and hole branch resistances from measurements and things like that. So we did like one by one. So we started with just 2 basic parameters, mobility and VXO. And then we started optimizing more and more and started to see where we get that best point. So 7 is, I think, total.
For these different channel length devices, you use the same compare resistance.
Well, it depends. Once you fabricate it, most of the time we interact with experimentalists to find out if their contact resistances have changed or their contact resistances have remained the same. But for some of these devices, we see a little bit variation in contact resistances. So I have an exhaustive table of extracted parameters, which I can show you. So the resistances over here were somewhere around 500 ohms micron. So yeah, but they go all the way up to like 1,000, 1,500. So I've seen a lot of variation.
So for this shorter channel one, the 40 nanometer one, the on-off ratio becomes so small. It's because of the large comparables.
Yes, these are very contact limited devices. For shorter channel lengths, we have not been able to successfully see any saturation effects. So another question that comes from this is, how do you know what your injection velocity is for these devices? So those are some very physical, fundamental questions that we need to ask ourselves. So we don't see any saturation, that's true. All right. We also looked at the S parameter measurements of all of these devices. The plot over here shows current gain versus frequency for all of the different channel length devices that we got from IBM. The different traces are for 40 nanometer all the way up to 650 nanometer. And the symbols are the experimental data, and the solid lines are our model. Please note that in our dynamic model, we are not introducing any additional fitting parameters. All the parameters have been obtained from the static transport formulation, and therefore our dynamic model is self-consistent with the static model. And the point where current gain becomes unity is the cutoff frequency. So we've been able to estimate the cutoff frequencies very nicely for these devices. And here we see the cutoff frequency versus inverse of the gate length. The symbols are the experimental data, and the red solid line is from our model, the quasi-ballistic model. So again, I went back and tried to use the drift diffusion formulation, which people have used a lot in the past. I saw that that model was not able to predict the cutoff frequency versus gate length behavior accurately. And this is also a signature of the fact that the transport in these devices is indeed quasi-ballistic. Also, we've been able to extract the ballisticity parameter that you can see in the inset of this second plot as a function of gate length. You see that the ballisticity parameter changes from about 0.1 to about 0.6 as the channel length changes from 650 nanometer to about 40 nanometer, which is expected because the shorter the channel gets, you expect it to be more and more ballistic. We don't yet have a good understanding on how this ballisticity parameter would change with the different mobilities and different mean free paths of these devices, which is again a question that we are looking into. All right. So,
One question here.
yeah.
So you are using the transistor as a current source?
Mm-hmm.
You are using the transistor as a current source, right?
In this is current gain, yes.
Current source.
Mm-hmm.
So basically, we don't see any saturation region in the curve, right? So if the saturation region is not there, how do you define output impedance?
That's a very good question again. So right now, the output resistances are very, very low for these devices, and these are very contact limited devices. So we extract the VXO from the devices and we hope that it is what we are really expecting it is. And that's a very open-ended question, and I don't have a good answer.
You don't get any output impedance here.
Mm-hmm. So we don't know if we can use it for logic or for those applications.
You actually have that problem, other problem that you don't have.
Yeah. So even for R0, I understand your point of how do you define an R0 for these devices if you're not seeing saturation. So R0 for us is directly related to VXO, which is the injection velocity, which happens in saturation. If there is no saturation, how do we define R0? So we extract VXO, and from that we go back and say, okay, if VXO is this is what our R0 would be. And we hope that that is the R0.
In the charge partitioning scheme, you said that you have used bond pattern partitioning scheme, which is valid in the quasi-static regime. But when you're using an RF circuit in the gigahertz range, you think that the device still is in quasi-static regime?
Well, for now, I don't know of any other good way to go and do this charge partition. People have talked about a lot of different kinds of charge partitioning schemes, and this is one of the charge partitioning schemes that I'm presenting. And maybe you can point me to other kinds of charge partitioning schemes that do exist in literature. So I know that there are plenty of those, and some that assign more weight to the source, and all those kinds of things. So
you talked about the top of the barrier, and the injection velocity. So, but when you don't have a band gap, where is the barrier?
Mark should answer that question.
That's always confusing me too.
So what my goal would be next is to study that potential profile and understand where the barrier is. But for that, we need a lot of quantum mechanical simulations, and the NEMO team at Purdue we should probably collaborate with them, and that is...
So I'm actually surprised it works as well as it works. It's beautiful fits, but there is no barrier in graphene, right? So there is no top of the barrier.
Exactly. So what we're defining as the top of the barrier or the virtual source point, we need to get a more physical understanding of it, doing all these profiling of the energy bands and things like that, which I hope I can work with people at Purdue and understand. And I've been talking with people, and it's a big question for us to understand that right now. Yeah. All right. So the next thing that we wanted to do was we wanted to understand some physically meaningful parameters for this graphene technology that I have been analyzing. And this is mean free path and effective mobility. So the apparent mobility, or the mobility that we extract from the VS model, can be given by the Mathiassen's rule of a ballistic mobility and an effective mobility that is valid in a long channel device. And the ballistic mobility varies with the gate length. It's linearly proportional to the gate length, as you can see over here, and there is the mean free path of the device. If you did a little bit of math, you can show that this inverse of mobility, which I'm getting from the VS model, can be expressed by the equation given over here. What am I trying to do here? What I'm trying to do here is I'll plot 1 over mu versus 1 over LG, and I hope to get a straight line. And when I get that straight line, the slope of that straight line can give me information on lambda over mu effective and 1 over mu effective. That is what I'm trying to do, and I'm trying to understand what is the effective mobility for this graphene technology that I have been analyzing, and what is the mean free path that I have been analyzing. All right, so this is what I'll do. This is a table of the mobility that we've extracted from the virtual source model, and this is the gate length. And I've plotted the inverse of the mobility versus inverse of the gate length. The symbols are these extracted mobilities, or the apparent mobility of this device. And we see that they fall very nicely on the straight line. So
Are these mobility experimentally extracted from the IV characteristics?
These are fitted, and we've actually gone back to the experimentalists. So what these people have done is they've measured, they measure their mobility in like a big channel device. So what they measure is an effective mobility, and sometimes people also do short channel mobility measurements, but I do not have any confidence in the way they extract their mobility for a short channel device, because there is this ballistic mobility effect which needs to be incorporated, and a lot of the time experimentalists fail to account for that. So these
Contact effects, are
they are included. All of them are included to extract these mobilities. So contacts, sometimes they give us the values and sometimes they don't. And it's again a question of how many parameters are you optimizing? What are you optimizing? Are you getting the right results and things like that?
So you think they use a two-terminal source strain measurement and try to take away the contact effects? Extract the
Yeah, but for these I didn't get any data from IBM on the mobility of the devices. So these are actually extracted from the virtual source model. Yeah. So we fitted that with a straight line, and what we get is the effective mobility of about 2700 centimeters square per volt second and a mean free path of about 175 nanometer for this particular technology. Next, we wanted to look at the ballistic velocity of these devices. So if we look at the saturation current from the VS model, we have an expression for the saturation current. And if we go back to Mark's model, which actually dealt with the reflection transmission coefficients, we have a model from that. And if we combine both the models, we can show that what we are extracting from the virtual source model can be related to the ballistic velocity by a simple expression given on the top right-hand side. The question is this lambda over here, which is the mean free path, does it remain the same in saturation conditions and the linear transport regimes? But we are assuming that it remains the same. So what I'll do from here is we have extracted VXO from our VS model, from the transport IV data. Then we plot 1 over VXO versus LG, and that we hope to, we hope that it falls on a straight line, and the y-axis intercept gives us the inverse of the ballistic velocity. So this is what we did. We have the inverse of the velocity versus the gate length. The table over here is the extracted parameters, extracted VS velocity, and the symbols over there are the same data that we extracted. And we see that it falls on a straight line, and we can come up with a ballistic velocity which is about 8.2 times 10 to the power 7 centimeters per second, and this is very close to the Fermi velocity of the graphene electrons. All right? So we've tried to somehow bridge the links between the virtual source model and the reflection transmission coefficient model that existed before through this exercise. Next, I'll go on to simulation of graphene frequency doublers. So this is a single-ended graphene frequency doubler, and we have a GFET that is biased to the Dirac point, and we give it an input frequency of f, and at the output we get the double the frequency, and then that is a differential ended topology where we have two symmetric graphene field effect transistors. And the difference between the differential and the single-ended topologies is this, that suppresses the feed forward of the fundamental component, and it also suppresses spurious components in your output. So as a frequency doubler, what I'm really hoping is to get double the frequency at the output, but I don't want a triple frequency component or other higher order harmonics. So that actually does a better job at that, and not only that, its amplitude of the double frequency is also higher, which I've tried to somehow show through a higher amplitude signal at the output. So we implemented the very log A model, and we ran spectral simulations, both time domain analysis and periodic AC analysis. And we see that differential topology performs better than single-ended topology in terms of the amplitude. But that's not the take-home message over here. What I want to drive over here is that our model yields continuous currents, charges, and their derivatives, and it is very suitable for using in analog circuit simulation. And we get a higher output signal with differential frequency doubler. That's always there. I won't be able to show you the analysis with the periodic AC. Yeah.
So did you consider the mismatch between those?
Yeah. So mismatch will actually make this go very bad. It's much worse for single-ended topology because it doesn't have a matching, transistor with it.
Even for that differential also?
Yeah, it will make it much worse. It'll make it much worse. Yeah. All right. Good. So to summarize part 2, we've developed a static transport model that is valid in both uni and ambipolar transport regimes. We've captured the asymmetry in current conduction because of the different electron and hole branch channel access resistances. We've developed a dynamic model that is self-consistent with the static transport model. It yields continuous charges and capacitances, and it's valid from drift diffusion to ballistic transport regime. And we've calibrated the model exhaustively with DC and S parameter measurements of GFETs. We've been able to extract mean free path, effective mobility, and ballistic velocity. We've also done some circuit simulations of GFET frequency doublers to demonstrate the model capability for circuit and system level analysis. So going back to graphene, what I personally think, what I would like to do in graphene in the future, and where I think that the whole field is really going. I mean, there are plenty of directions that one can take. I'll talk about solar cells and photonics, photodetectors and optical modulators. So graphene can be used in photovoltaics, which basically deals with converting light energy into electrical energy, and graphene has potential to be used in low-cost, flexible solar cells because of its advantages like high transparency, invisible, mechanical strength, and flexibility. I think that there have been plenty of experiments, particularly ones that are being done at MIT in Jing Kong's group, that actually use graphene as the top electrode, but I still feel that there is a lot of gap between modeling and simulation and experimental efforts in this particular technology. And I think modeling would be able to address some of the unique challenges of this technology as to how graphene interacts with the substrate, with the organic substrate in particular. I've done work on interaction of graphene electrons with different kinds of inorganic substrates, but it would be important to understand how it interacts with organic substrates, how does it couple with contacts. Contacts have been a very daunting challenge for this technology. And also how multilayer varies as a multilayer transmission coefficient varies with the number of layers. That is something which we need to understand because, as I've shown for the interconnect applications, multilayer has better resistance or lower resistance compared to single layer graphene, which is important, and that would also be very useful for solar cell technology. And my aim is to guide the experimental research in this in the right direction and also learn something from them so that we can finally highlight the major challenges, limitations, and opportunities of this very important technology. The next thing is coupling of graphene and light. I think integration of graphene photonics within a silicon photonics platform is a very important research direction. And in this hybrid circuit, the passive components such as light routing and guiding can be implemented in submicron silicon waveguides, whereas the active elements such as modulator and detectors can be implemented with graphene, and also the analog circuitry can be implemented in graphene that drives these photodetectors. And I think one of the reasons why I'm proposing this is because graphene has a very strong light-matter interaction in the mid and far infrared frequency range, which has typically been considered as the frequency gap between electrical and optical systems. And I think that graphene can be used for terahertz communication and spectroscopy, mid and far infrared imaging, and all those things. But there are plenty of challenges. The first challenge that I think is on the physics and scalability side. We don't really understand the intra and interband absorption in graphene very well. We've been using the conventional Drude formula to analyze the optical conductivity of various materials. We don't know if that would be applicable in graphene. That's the first question. The second is, how does graphene couple with the plasmon? How do plasmons in graphene couple with the substrate? How does the effect of the ribbon width change the dispersion relationship of these plasmons that exist in graphene? So those are some of the physics and scalability related questions. And the second part, if we really want to do this heterogeneous integration and build a hybrid circuit, simulation capabilities are lacking. That is one of the biggest challenges. Verilog K has catered exclusively to electrical circuits community, and we don't have a very good way of representing photonic quantities in their native natures and disciplines. And I think attacking the problem bottom up would be a good idea, where we can actually represent some of these photonic quantities in a very natural way. And that would actually assist in the circuit and system design. And finally, this is my last slide, and I think that graphene has ushered us into this two-dimensional nanoelectronics research era, which would play a very important role going forward. I think we need to understand the applications of 2D materials outside of logic. Could be flexible electronics or optoelectronics, for instance, There are plenty of challenges, as I have experienced from my experience in interconnects and RF circuits. There is a small density of states, the coupling of 3D contacts to two-dimensional contacts, top contacts versus side contacts, Schottky barriers, question of top of the barrier, does that really exist, things like that. And then how do you do dielectrics on 2D materials and gate control. And finally, I think that we need the development of new simulation capabilities that are specifically tailored for 2D materials. And this should be very much coupled to the experiments so that we can understand, we can leverage the experimental results and build our theoretical models better, and also leverage some of the opportunities that exist here in terms of NEMO and things like that, where we can understand what is truly going on in this area. And that would be a very interdisciplinary outreach, I believe, to usher us into this differentiated and accelerated technology innovation of the future, which is what Dennis Buss calls it. Thank you very much for your time and attention.
So time for a few questions. So from my experience, it seems the virtual source model, the contact resistance is a big parameter, right? You mentioned you got it from measurement.
You could get it from measurements.
So how you measure for holes and for electron are different? How you measure?
You can't.
You can't?
I don't think so. You can bias your device either in the electron branch and hole branch and try to accurately extract your source and drain resistances. But I don't know, York, do you have I think you have worked in extraction of contact resistances and things like that. So do you think that experimentalists would be able to understand that there are differences in electrons and holes?
Well, we have proposed a model where we're trying to say, John had worked on that as well, with different contact metals. If you're using top and back gate, then you can really shift the respective curves, namely the curve that comes from the contact gated region and from the middle gated region relative to each other, and can really disentangle those resistance contributions. So I think in general there is a way to get a handle on the experimental component that is underlying this contact resistance.
And I also think that mobility measurements are not being done accurately for short channel devices. I think you have a very nice paper in IEDM that talks about how to do this accurately for short channel devices by removing the effects of this ballistic mobility and things like that. So, yeah.
So speaking of ballistic transport, so do you think that this parameter that you kind of alluded to, this zeta parameter, is something that's fairly well reproducible across a broad range of samples, or is it just each experimental procedure is going to produce its characteristic zeta? Because I think at least you seem to be assuming that zeta was uniform across a set of devices with different channel lengths.
Now, zeta actually scales with channel length. So the shorter you make your channel length, zeta becomes higher because zeta is ballisticity, and the shorter so you have to compare your channel length with the mean free path for that technology.
Can you go back to that?
Yeah, sure.
Because I think, okay, so you wrote that zeta equals 30%.
Oh, that I was just doing for one simulation. I just wanted to show you one particular simulation of what a quasi-ballistic charge model would do and what a drift diffusive charge model would do, and that was only for one channel length device.
Okay,
so I'll go back to
zeta is not really a specific parameter that you're fitting, because you said there are 7 parameters that you were fitting. But that's not...
Zeta we are actually extracting from only the S parameter measurement. So zeta is the only factor that we get from this measurement. While rest of the transport parameters or rest of the parameters that go into the dynamic model come from the transport formulation. So this is the only one that we extract from this. So if we didn't have that, we would not be able to reproduce this very nice fitting that we see over here. So that ballisticity that you see, that varies from very low to very high, and it has to be between 0 and 1. Now the big question is, how does it scale with the mean free path, or will this be generic? Will this be reproducible? I don't have answers to those questions, and I would hope that it is reproducible and that we always see this. It also depends on how people are doing their measurements for this S parameters, because the moment you change your bias voltages, you can shift from electron branch to hole branch. And then even though you would want to see that behavior, you will not see that behavior. And in fact, I was talking with IBM and they did their measurements on the hole branch for this. And hole branch for these devices has higher resistance than electron branch. And they didn't do their measurements on electron branch, and it feels very strange to me because IBM always wants to publish the highest cutoff frequencies. And I went back to them and I said, you know, my model shows that your electron branch should have had higher cutoff frequency. Why did you not do that, produce that in your Nature paper? And they said, oh, we didn't realize, because what really happens in these devices is cutoff frequency increases. As you start coming close to ambipolar transport, it decreases in ambipolar, and once you go to electron, it again starts increasing. So once they started seeing this decrease in cutoff frequency, they stopped doing their measurements, thinking that it would be a uniform trend and it would exist forever. So they didn't understand the issue of modeling behind it. And I go back to them and ask them, can you go back and do the measurements on electron branch? So I have to push them very hard to do it, but hopefully maybe they will in future. I don't know.
Well, that would be an interesting test of the model. Turns around and goes back up.
Yeah, it would be the best test for the model, because that's what my model tells me, that the ambipolar part has very high capacitance, so you are expected to go down in frequency, but then again you will pick up in frequency.
So normally they do measure the GM as a function of gate voltage.
They didn't cross the ambipolar. Yeah, they do, but in this case we didn't have GM measurements.
And other questions?
So you showed the IV curve in the graphene field, and it was asymmetry in the electron branch and hole branch. And you said that it is because of the different coupling to electrons and holes. But when the band structure is symmetric, you know, the electron and hole have the same effective mass, and it's like you cannot say actually is it electron or hole.
Now, what really happens in these devices is that the contacts tend to dope graphene underneath the channel. So most of the times contacts will dope it either N-type or P-type, so that when you actually go from, in the channel, if the carriers change from N to P-type, there's an NP junction or a PN junction that gets formed. And that is different for electrons and that is different for holes. So if it's a PN junction, obviously, you know, it's not a good thing. If it's a PP junction, it's a good thing. Or an NN junction, it's a good thing. So.
Yeah, but could you, for example, say, you know, you push the Fermi level from 0 to below 0, yeah? So this asymmetry comes from that change in
the potential barrier height at the contact. If you have to understand that very clearly, you have to see how the potential profile changes underneath the contact and how it keeps changing in the channel. So that change is different for electrons and holes.
Okay, so I'm going to jump in as my role as seminar chair and ask for one more question, because we have a packed agenda for you. So it's nice to see all of these questions, but I don't want it to get too far behind with the rest of the schedule. So you want to ask that?
So coming back to the channel length scaling, that the output characteristics actually show smaller and smaller on-off ratio. And from your physical model extraction, can you tell me the physics behind it, why the on-off ratio actually gets smaller when the channel length?
I think that this is a very good question, and I think that in these devices it gets limited, and it's a very involved philosophical question right now for me. And I think that contacts tend to play a bigger and bigger role as channel length gets shorter and shorter.
So you said here you actually have different channel.
Yeah. But still, if the contact resistance is not scaling at all with channel length, and you make your channels shorter and shorter, the overall device tends to get limited by what the contacts are really doing. So contacts are not becoming any way better with technology, with gate length scaling in this particular case. And then again, the question is, if graphene does not have a band gap, then why does it even saturate for longer channel devices?
Have you simulated the IDVG? When you see the smaller on-off ratio, do you all blame the on-state or do you also blame the off-state?
Oh, that's a very good question. I think I probably will have to go back and check how these keep changing with the on-off ratio, because we're really not targeting on-off ratios over here. We really because these have very poor on-off, maybe 3 or 4, something like that.
Yeah, because you simulated you
So yeah.
Okay, so thank you for a very interesting talk.